let me just ask you a very simple question, right? So what is the first thing that comes to your mind when you hear the carbon dioxide? It's a greenhouse gas, right? The ultimate thing that comes to your mind is global warming, right? And this will lead to polar ice melting, and this will lead to increase in sea level, and this will actually lead to the extinction of the species. But the real question is it that bad? So in order to find out that, me and my team, here at IIT Kanpur, under the guidance of Dr. Suman in the Department of Mechanical Engineering, we try to find out the good aspect of carbon dioxide, right? So let us look at the P2 diagram of the carbon dioxide. So you can see this is normal pressure graph of the carbon dioxide. You can see there are three phases, solid, liquid, and gas, right? This is CO2 is a bit bad, you can say, in this region, but there is a specific reason, right? This is called supercritical CO₂. So the CO2 behaves very differently, I would say very chaotically in this region, and it also has some good behavior in that region. So we are supposed our main aim of the experiment is to take CO2 from the normal to that area and visualize how it behaves, and also validate using some established theory related. So when you find out this graph, then you see the graph point. This is a triple point. You all know this is a equivalent point in a PT graph where all the three phases coexist. So initially you take a dry ice. I put this in the water to have a great visualization. Initially it has a minus 40 degrees Celsius at 1 bar, and we are supposed to take this dry ice to supercritical region. So while doing so, we will be following this path. So we enter the supercritical region through these points. Okay. As you can see, the supercritical point, which is 13.1 and 75 bar. Right? So 31.1 is quite decisive, but 75 bar is a very high pressurized chamber. Right? In order to get to that pressure, we are supposed to fabricate very high pressurized chamber. So what is the first thing we do whenever we fabricate something? We model it, right? So I have modeled this in metal modeling. This is 3D model, and we will just show you a very quick video of how we disassemble this 3D model. There are some nuts and bolts. There is a flange to keep the pressure on. This is an acrylic transparent plate. This is a gasket. It's a base holder. It's a heating pipe. That's a pressure gauge. That's a thermophysical. And this is a aluminum heating pipe, right? These are the specification of this particular chamber is that we operated in the region of minus 40 degree to 40 degrees Celsius, and it has a maximum gauge pressure of 100 bars. You can achieve that pressure also. And it is also PID controlled heating, and we use it, and also use ceramic acid and K-type thermocouples. Now, let me just show you my 6 months of work in only 50 seconds. So, please have a look at it. Now this is heating, right? So we are supposed to put 31.1. Have used controlled. So we have a set value of 32 degrees Celsius in PID2. As the heating is happening radially, as you can see, the liquid is getting converted to gas. When the critical is going to attain, this interface will disappear. Very good. And this is the onset of critical point, right? And this is remember this circulation happening. Will be answering this. So after the reaching the critical point, you also trace it back by cooling it. So I have used 25 degrees Celsius in the PID control in order to cool it down. So while cooling back, we are able to see some very great visualization of direct condensation of gas CO2 directly into the liquid one. Let's move ahead. Now let us validate our experiments, right? We use some established theories and correlations. Yeah. So let us look at the theory part. Basically, this is the plot of all the thermophysical properties. I have plotted this one using mixed values, and so mainly thermal energy. What excites me more is the increased value of Cp, right? There is sharp increased value of Cp. So as you all know, the Cp is nothing but the ability to heat, store the energy in form of heat. So if we somehow could use this, use this supercritical fluid as a energy storage, that would be great. And it also has some properties like which has gas-like diffusivity and density, which enables it to go to a very small pores also. This can be used in the decaffeination of the coffee, right? So next time whenever you go to some coffee or cafe, caffeine, ask for decaf coffee instead of normal coffee. We will free from caffeine one, right? And yeah. So what is the daily unit convection? So whenever there is a heat body, there is natural convection, right? But daily unit convection is very specific type of convection where the temperature gradient is from low to high, whereas the gravity gradient is from higher to lower, right? This initiates something called range unit convection, and the formula for that is G beta delta K equal to alpha. So here first we heated it, right? So the entire system has 31.1, and when you cool it down, the outer one is at 25 degrees Celsius, but the center one is still at 31.1. And this imitates the Rayleigh unit convection, and this is the reason why you are able to see the circulation happening inside the chamber at the critical point. So let us look at the Rayleigh number here. As you know, this gravity, beta is thermal expansion coefficient, and delta T is Rayleigh number. So this is quite interesting, right? As you can see, at critical point, this mu and alpha that decrease very sharply, right? So in order to have a constant Rayleigh number, the L has to be very small. This simply means that the characteristic length will be very much less. This indicates that the circulations will happen within a very small dimension, a small characteristic length, and this what causes something called critical openings. You can see this milkiness inside the happening. This is due to this decrease in the L scale to have a good presence in it. This is called critical openings, and this is also milkiness inside. So this is very down in the experiments. Now we will move to the ANSYS modeling. So I have used I have compared the heat transfer coefficient in normal condition before the critical point, after the critical point. As you can see, so let us look at the before in normal conditions. So I have used water in ANSYS modeling, and you can see the look at the heat transfer coefficient, the maximum one. Here it is only 1.2 to 10%. It's around 1200, right? So just before the critical point, it reaches to 14,000, right? And at critical point, it reaches to 35,000. So there is a rigorous, I would say, heat transfer is happening inside the chamber, right? You can see to have a constant Rayleigh number. This is the average H bottom and H top. With this, thank you all. And if you have any questions, I will be happy to answer your